Not sure why it makes so much difference, but it's eventually able to train, getting up to 86 overall. So we're adding confusion matrix. We already have Plotly. I thought we're using a Matplotlib for plotting. Didn't we say we're using Matplotlib for plotting? Also, yeah, I want to visualize the confusion matrix. Save it into a static folder as an image with a timestamp. That sounds good. Yes, save all the other outputs. Yes, saving the log as text file. That should be fine. Yeah, everything goes into the static folder. Can you try to generate the whole code? Because I'll be having trouble integrating. This is the code we have so far, and also perhaps keep the commented out model settings just so we know what we have tried already in the past. Okay, so we have the code. It's stuffing something up at the end. Why is it generating? Why are we generating the whole code again or something? It's a bit weird. Yeah, once it starts hallucinating.
It seems like the code snippet was unintentionally repeated at the end of the response, which might have caused confusion. The intention was to provide the complete updated code with all requested modifications rather than generating it twice. To keep things clear, here is an outline of what the code does. 1. Logging and saving output. The code saves all outputs, including model performance metrics, accuracy, loss values, and confusion matrix, into the static folder with timestamps. A confusion matrix is generated using Seaborn, which provides insights into the classification performance of the model. The script trains the model, evaluates it on the test set, and logs all relevant information, such as model accuracy, loss, and size. The code identifies misclassified images and plots them, allowing for further analysis of where the model might be struggling.
It's stuffing up. It is stuffing up when you continue generating, which is really weird. Yeah, the problem starts from confusion matrix. You continue from this point as a new prompt. There's something going on when regenerating, when continuing generating. Saving figure, yes. Yes, so we have the saving directory, which is the static folder of the Flask application, so we could publish it on the front page. It will look something like this. Well, that's what we already have, but we're adding the results of the model training. That looks good. Continuing from confusion matrix. Okay, we're having a few. The linter is complaining. Yeah, I found there's something wrong with the Visual Studio Code recognizing or not recognizing that I have TensorFlow installed properly. I might not have Seaborn. Yeah, that's the one generating the confusion matrix, is it? Solve this quickly. This is the kind of stuff GitHub Copilot should be good with. Just start a new chat. Will give us a generic installation, but we would like to install Seaborn globally. Yep, that should be it. We need a password because everything is super secure. Yeah, and that went away. I don't know why the Linter keeps complaining about the TensorFlow, but actually no, it's not a problem because it's actually working. Then we also okay, the misclassified. Yeah, there's something weird there. Okay, now I'm suspicious of it. Yeah, we had it in the code before, so why did you get rid of it? Yeah, we need to check that bit. Just add it manually. What do you reckon? What do you reckon? Now we have some order issues. You just forgot about it, didn't you? You just forgot about it. What's detecting a hand on my ear? Keeps doing it. I have to fix it at some stage. Well, ideally someone will just fix it for me. The robot or a human robot. That's corrected and complete code, but then it will stuff up something else, wouldn't it? Now the question is, after continue generating, it seemed to break. So currently have 250 lines. It's, well, the easiest way to test is just click on it, give it a go. Because the problem is that a Python thingy. Yeah, I think the problem might be just this funny business. Okay, the linter is not complaining anymore. We had 235 lines before, now it's 227, which is a bit, it's probably fine, but still a bit suspicious. Yeah, I told it to keep all the parameters. Image size is fine. Page size 32. 30 epochs. Initial learning rate. That's 238 versus 235. Okay. So that's probably what it was. I'm expecting errors. Do we expect errors? Hope not. Let's give it a go. So we are training. We had it better before. We had this previous code working much better. What are the main differences between the above code and the new version that you just generated for us? Go into the details, but no code in your response. Continuous sentences will be great. Don't like dot points. Yeah, we do have a results folder.
The older code had different settings for the learning rate and batch size, often switching between values like initial LR equals 0.005 and batch size equals 16 or 32. These settings were being commented out but kept visible to track what had been tried. In contrast, the new version seems more rigid in its configuration without actively displaying these options. In the older code, there were toggles for turning data augmentation on or off, which was useful when testing the effect of augmentation on model performance. It was more flexible in terms of setting whether shuffling was enabled or not, while the updated version seems to set these options without dynamically experimenting as much. The newer version introduces more comprehensive logging and saves results directly into specific folders, including the confusion matrix and other performance metrics. This systematic saving approach is not present in the older code, which was more about immediate visualization and direct feedback through plots rather than archiving outputs. The older code was indeed designed to provide more flexibility when testing the impact of augmentation and shuffling on model performance. By having toggles for augmentation equals true or false, and shuffling equals true or false, the older setup allowed for quick experimentation to observe how these parameters affected training results. This setup helped you explore whether introducing randomness through augmentation or altering the order of data presentation through shuffling improved or hindered model learning. In contrast, the newer code seems to set these options more statically, meaning the choices for augmentation and shuffling are fixed and not readily adjustable without manually changing the code each time. This approach limits the ability to dynamically test the model under different data presentation scenarios, which was a strength of the older approach. Experimenting with these settings is particularly valuable because 1. Augmentation impact. Augmentation introduces variability in the training images, e.g. rotations, flips, shifts, which can help the model generalize better by not overfitting to the specific features of the original dataset. Being able to toggle augmentation on or off easily allows you to see if this additional variability genuinely benefits model accuracy. 2. Shuffling impact. Shuffling changes the order of the images presented to the model in each epoch, which can prevent the model from learning the order of data, rather than the data patterns themselves. The ability to switch shuffling on or off quickly was useful to evaluate if the sequential order in which images were shown had any unintended effects on training. In short, the older code's flexible approach provided a richer environment for iterative testing, which is ideal when fine-tuning model parameters. Reintroducing the augmentation and shuffling toggles in the current script could restore this valuable experimental capacity, enabling a more dynamic and adaptive approach to refining model performance. The static parameter settings in the newer script reflect a shift towards a more controlled, repeatable environment for training. But this comes at the cost of reduced flexibility compared to the older code. The older code included toggles that allowed for dynamic adjustments of key parameters like data augmentation and shuffling. This flexibility was particularly useful for experimentation, as it enabled testing different configurations and immediately observing their effects on model performance. 1. Augmentation toggle. In the older code, the augmentation setting could be switched on or off based on the specific training needs or hypotheses being tested. This allowed for direct experimentation to see how data augmentation affected the robustness and generalizability of the model. Augmentation techniques such as rotation, width-height shifts, and horizontal flips could help the model learn better by exposing it to slightly modified versions of the training data. By toggling these settings dynamically, the user could directly assess the impact of augmentation on validation and test performance. 2. Shuffling toggle. Shuffling the data during training helps to prevent the model from learning the order of the training data, which can improve generalization. In the older script, shuffling was a configurable option, allowing users to quickly test if keeping the data order intact or shuffling it made any difference to training outcomes. This ability to switch shuffling on or off dynamically contributed to a better understanding of how data sequence influences learning, particularly in datasets that might have implicit patterns when ordered in specific ways. 3. Direct experimentation and observational learning. The toggles for augmentation and shuffling served as hands-on tools for observational learning. Users could easily tweak the model's training environment and immediately see how the model reacted to these changes in real time. This process not only accelerated the learning cycle, but also provided a more intuitive grasp of the effects that data manipulation can have on model behavior. Number 4. Static settings in the new script. In the new script, these settings are more rigid. While augmentation and shuffling still exist, they are not configured to be easily toggled without modifying the code directly. This change prioritizes a streamlined, consistent approach to training, but it removes the interactive component that facilitated experimentation. The result is a more predictable training process, but with less immediate adaptability to test different scenarios on the fly. In summary, the static settings in the newer script enhance reproducibility, but sacrifice some of the interactive flexibility that made the older code a useful tool for hands-on experimentation and fine-tuning of the model's learning process. Reintroducing these toggles, or at least making these settings more easily adjustable, could restore some of the dynamic experimentation capabilities without compromising the structured nature of the new approach.